Hello, we are Abhay and Saurabh, and today we will be discussing about static code analysis. Static code analysis is the process of analyzing software systems without actually running the code. The analysis is usually done on the source code and in cases object code or bytecode as well. As part of our software engineering project, we analyzed two very popular static analysis tools, FindBugs and PMD. We will be discussing the details of both of these tools. Also, we ran both of these tools on two open source code bases, Eclipse and iTrust. Both of these code bases are in Java. Okay, so the first tool we analyzed was FindBugs. It is a very popular static analysis tool that looks for bugs in Java programs and is based on the concept of bug patterns. A bug pattern is a code item that is often an error, such as null pointer dereferences, infinite recursive loops, bad use of the Java libraries, and deadlocks. Find bugs work on Java bytecode rather than the source code. The plugin for find bugs are available for Eclipse, NetBeans, etc. Find bugs is released under LGPL license. It is written in Java and comes with a standalone GUI. However, the command line interface and plugins for Common ID are also available. It aims for the detection of real bugs, unlike some other static analysis tools that focuses on violation of coding conventions and tries to advocate the uses of static analysis in software development by making it more accessible. The rules range from general bad practices to the correctness of multi-threading and vulnerabilities to attacks. Violations generated by FindBugs are classified in three categories: correctness, bad practice, and dodgy. Correctness violations are those that represent an apparent coding mistake resulting in code that was probably not what the developer intended. Correctness bugs include wrong type handling, like casts that are guaranteed to fail, or instance of checks that are always true or false, respectively. Also, it detects null dereferencing that seems certain to occur should control reach the code. Likely logic errors are detected where statements do not have an effect or calculation will always have the same result. Rules also perform correctness checks which are simply not covered by the compiler. The creation of self-containing collections, invalid regular expressions, and format strings, apparent infinite loops, and loss of precision when operating on numbers. Bad practices are violations of recommended and essential coding practices. Examples include hash code and equal problems, clonable item, dropped exceptions, serializable problems, and misuse of finalize. Third violation is dodgy, which represents code which is written in a confusing way and is therefore less transparent and robust. The patterns are similar to those in correctness and bad practice categories, but more false positives are accepted. Dividing the violations into these different categories is very helpful for a developer as it gives him an idea about the possible severity and can prioritize the fixing of these violations based on the available time. Now my partner Saurabh will be continuing with the discussion.
Thanks, Abhay. The other tool that we analyzed is PMD. PMD is a source code analyzer. It finds common programming flaws like unused variables, empty catch blocks, unnecessary object creation, and so forth. It supports Java, JavaScript, XML, XSL. It also includes a copy-paste detector, CPD, which finds duplicated code using the Rabin-Karp string search algorithm in various languages like Java, C, C++, C Sharp, PHP, and Ruby, etc. What PMD gives us are not true errors, but rather inefficient code, meaning that the said application could still work properly even if they were not corrected. When we ran PMD on a Java source code, it helped us to identify the following categories of potential problems: identifying empty try, catch, finally, and switch statements. Dead code, which are the unused local variables, parameters, and private methods. Suboptimal code, meaning wasteful string or string buffer usage. Overcomplicated expressions, like unnecessary if statements, for loops that could be while loops. And lastly, duplicate code, like copy pasted code. PMD includes a set of built-in rules and supports the ability to write custom rules. The custom rules can be written in two ways: using XPath and using Java classes. Some of the rules that comes with PMD are unused code, which is always bad. Another rule is to check if nothing is being done in either the then or else block of the if statement. Third rule is creating a new string object when things can be done just by assignment to a new string variable. The fourth rule is naming. Rules in this category describe naming conventions listed in the code conventions for the Java programming language. And the last one is the code size rules. Examples are overly long classes, methods, or parameter lists. Many fields or methods and code that has a high number of decision points or execution paths. PMD tool classifies the bugs in the following categories: blocker violations marked red, meaning that it is of the highest priority. Critical violations marked cyan are the next highest priority. Urgent violations are marked as green, important violations are marked pink, and warning violations are marked as blue. A major limitation that we found in PMD during our analysis was that though PMD can detect and report bugs found by matching AST patterns on source code, but when analyzing the source code, PMD provides very limited type information to the rules. In fact, the types of objects often are not determined by PMD. This makes it difficult to implement rules in PMD that refer to the types of objects. You can find more details about the internal workings of Findbugs and PMD in our blog post at http static code analysis tools.blogspot.com. For our better understanding of these tools and their efficiency, we ran the two tools Findbugs and PMD on Eclipse and iTrust source code basis. iTrust was founded as a class project for software engineering at North Carolina State University. It is a health application that helps patients to keep up with their medical records and is also an interface for medical staff from different locations. The details of the number and types of warnings generated by these two tools on the two source codes can be referred in our blog post. Following are some of the important comparisons between PMD and Findbugs based on our findings. PMD has a large rule set and it helps to find a large number of coding practice violations than Findbugs. Also, false positives were less in PMD as compared to that of Findbugs. This might be due to the fact that while PMD looks for coding conventions, Findbugs tries to find real bugs in the code, thus leading to larger set of false positives. We observed that the prioritization of violations in both these tools is coarse-grained, and the prioritization group includes many warning categories. There is no way to prioritize warning categories in the same priority group. To conclude, we would like to say that as a developer, you should admit that the code you write is going to have errors, and it is important to want criticism of your code. Thus, we believe that using static analysis tools is definitely worthwhile. These tools, though difficult and tedious to adapt at first, complements the traditional quality assurance methods like code reviews and manual testing. It is important here to mention the fact that the absence of warnings or errors in the static code analysis does not suggest that the code is free from bugs. The code still needs to go through the testing phase. Also, our analysis showed that find bugs and PMD is different kind of errors, and thus they should be used together for maximum benefits. That is all. You can check our blog post and screencast for more details. Thank you.